Welcome! In this video, we'll be tackling LeetCode problem number 849, maximize distance to closest person. This problem challenges us to determine the maximum distance between any empty seat and the nearest occupied seat in a linear row. It's a great problem to enhance your understanding of array traversal and edge case handling. Let's dive in. In this problem, you are given an array called seats, where each element represents either an empty seat, denoted by 0, or a seat occupied by a person, denoted by 1. Your goal is to determine the maximum distance between any empty seat and the closest occupied seat. The distance between two seats, located at indices I and j, is defined as the absolute difference of their indices, or abs, I, j. For the input, the array seats has a length n that is between 2 and 10,000, and it is guaranteed that the array will always contain at least one 0 and one 1. The output is a single integer, which represents the maximum distance to the closest person from any empty seat. This problem requires calculating that maximum distance efficiently, given the constraints. Let's look at an example to better understand the problem. Suppose the input array is seats equals 1, 0, 0, 0, 1, 0, 1. In this case, we need to compute the distance to the closest person for each empty seat. For the seat at index 1, the closest person is at index 0, making the distance 1. For the seat at index 2, the closest person is also at index 0, resulting in a distance of 2. For the seat at index 3, the closest person is at index 4, giving a distance of 1. Among all these empty seats, the maximum distance to the closest person is 2, so the output is 2. Another example is seats equals 1, 0, 0, 0. Here, the empty seats are all at the end of the array. For the seat at index 1, the distance to the closest person is 1. For the seat at index 2, the distance increases to 2, and for the seat at index 3, the distance is 3. Therefore, the maximum distance is 3, which is the output. To clarify further, consider another example where seats equals 0, 1. In this case, there is only one empty seat, located at index 0. The closest person is at index 1, so the distance to the closest person is 1. As there are no other empty seats, the maximum distance is simply 1. Now, let's turn our attention to the constraints. The array length n is always between 2 and 10,000, and each element of the array is guaranteed to be either 0 or 1. Additionally, it is guaranteed that every input will contain at least one 0 and one 1. These constraints ensure that we always have both empty and occupied seats to work with, and they also indicate that we need an efficient solution to handle the larger input sizes. When solving this problem, there are a few edge cases to be mindful of. First, consider the scenario where all empty seats are at one end of the array. For example, in seats equals 0, 0, 0, 1, the distances to the closest person increase as you move farther from the occupied seat. Next, think about cases where empty seats are surrounded by groups of people. For instance, in seats equals 1, 0, 0, 0, 1, the middle seats will have smaller distances to the closest person compared to the seats at the edges. Finally, if there is only one empty seat, such as in seats equals 1, 1, 1, 0, 1, the solution simply comes down to finding the distance to the nearest occupied seat. By considering these edge cases, you can ensure your solution handles all possible scenarios correctly and efficiently. To solve problem number 849, the goal is to maximize the distance between an empty seat and the nearest occupied one. While the problem may seem straightforward, the real challenge arises from doing this efficiently for larger arrays. One approach we could consider is the brute force method. Here, for every empty seat, we calculate its distance to the nearest occupied seat by iterating both left and right across the array. While this approach is simple and requires no extra space, it has a significant drawback. For every empty seat, we may end up scanning the entire array. This means the time complexity is n squared, making it impractical for larger inputs. So, while it's a good starting point, we need something faster and more scalable. To improve efficiency, we can use an optimized approach that involves two passes through the array. The intuition here is to calculate the distance to the nearest occupied seat by performing separate left-to-right and right-to-left traversals. During the first pass, we record the distance from each seat to the nearest occupied seat on its left. In the second pass, we update these distances by considering the nearest occupied seat on the right. By the end, the maximum value in our distance array gives us the result. This method has a time complexity of O(n), as we traverse the array twice, and a space complexity of O(n) for storing distances. It's much faster than brute force and easier to implement than some alternatives, though it does require additional space. Another refinement is the one-pass approach, where we dynamically calculate distances to both the left and right as we traverse. This eliminates the need for extra space, achieving O(1) space complexity. However, it's slightly harder to implement since it combines both calculations into a single loop. For this problem, we selected the two-pass approach as the optimal strategy because it strikes the best balance between efficiency and clarity. One key observation is that the distance to the closest person is determined by the smaller of the distances to the nearest occupied seat on the left and right. By separating these calculations into two distinct passes, we simplify both implementation and debugging. The brute force method, with its O(n)² time complexity, is simply not feasible for larger inputs, while the one-pass approach, though more efficient in space, is less intuitive and more error-prone. The two-pass approach, on the other hand, uses O(n) space but ensures a clear and maintainable solution. It handles edge cases well, such as when all empty seats are clustered at the edges or in long sequences. Overall, this method provides an excellent balance between simplicity, efficiency, and robustness, making it the ideal choice for this problem. The problem asks us to maximize the distance between any empty seat and the closest occupied seat in a row of seats represented as an array. Each seat is either occupied, denoted by 1, or empty, denoted by 0. The task is to find the largest possible distance between an empty seat and its nearest occupied seat. For example, if all empty seats are at the ends of the row, the distance is simply the gap between the farthest empty seat and the nearest occupied seat. Conversely, in scenarios where all seats are occupied, the maximum distance would be 0. With these constraints and edge cases in mind, we aim to develop an algorithm that efficiently computes the solution for arrays as large as 10,000 elements. To tackle this problem, we use an optimal two-pass linear scan. The goal is to calculate the distance to the nearest occupied seat for every empty seat. This is achieved by scanning the array twice, once from left to right to compute distances to the closest occupied seat on the left, and then from right to left for the closest seat on the right. These results can then be combined to determine the minimum distance to the nearest occupied seat for each empty seat. In the first pass, we initialize an array called left to store distances to the closest occupied seat on the left. A variable closest tracks the last seen occupied seat, and if no occupied seat has been encountered, we treat the distance as infinity, represented by the array size. As we iterate through the seats, we update closest whenever we encounter an occupied seat and calculate distances for empty seats based on their position relative to closest. The second pass mirrors the first, but this time we scan the array from right to left to calculate distances to the closest occupied seat on the right. We initialize an array right to store these distances and use a variable closest to track the index of the most recently seen occupied seat as we move backward through the array. For each seat, if it is occupied, we update closest to the current index. If the seat is empty and closest has been set, we calculate the distance as the difference between closest and the current index. If no occupied seat exists to the right, the distance remains as infinity. After completing both passes, we iterate through the array once more to combine the results from left and right, calculating the minimum distance to the nearest occupied seat for each empty seat and keeping track of the maximum distance encountered. The two-pass approach is key to solving this problem efficiently. By separating the calculations for the left and right distances, we ensure that each seat is processed in constant time during each pass, leading to a linear time complexity. This approach avoids the inefficiencies of a brute force method, which would require recalculating distances repeatedly. For edge cases like empty seats at the ends of the array, the initialization of closest ensures that distances are handled correctly. Additionally, when all seats are occupied, the algorithm naturally returns 0 since there are no empty seats to process. This method is optimal because it minimizes redundant operations and ensures that we achieve the desired result in O(n) time. The algorithm relies on three key data structures. First, the left array stores the distances to the closest occupied seat to the left of each seat, computed in the first pass. Second, the right array holds the distances to the closest occupied seat to the right, calculated in the second pass. Finally, a single variable, max_distance, keeps track of the largest minimum distance encountered during the final iteration. These data structures work together to ensure that the solution is both efficient and easy to implement. The pseudocode outlines the implementation of this approach. We begin by initializing the left and right arrays with default values representing infinity. During the first pass, we iterate through the seats to compute distances to the nearest occupied seat on the left, updating the closest variable as we encounter occupied seats. Similarly, the second pass computes distances to the nearest occupied seat on the right, again using closest to track the most recent occupied seat. Finally, we combine the results by iterating through the array and calculating the minimum of the left and right distances for each empty seat. The maximum of these minimum distances is stored in max_distance, which is returned as the result. The algorithm achieves a time complexity of O(n), as each of the two passes and the final iteration through the array are linear operations. This makes the approach highly efficient even for large arrays. The space complexity is O(n), due to the left and right arrays, which store intermediate results for each seat. Overall, this method strikes a balance between simplicity and efficiency, making it well suited for the problem constraints and ensuring optimal performance. This Python implementation solves the problem of finding the maximum distance to the closest occupied seat in a row of seats. The method max_dist is defined inside the solution class. It takes a list seats as input, where 1 indicates an occupied seat and 0 indicates an empty seat. The function returns the maximum possible distance to the nearest occupied seat for any empty seat. We begin by initializing two variables, max_distance to keep track of the maximum distance found and last_occupied to store the index of the most recently encountered occupied seat. Initially, last_occupied is set to -1, indicating no occupied seat has been seen yet. The length of the seats array is stored in n. The algorithm proceeds in two passes. In the first pass, we iterate through the seats array. If we encounter an occupied seat, seats I == 1, we check whether it is the first occupied seat. If so, the maximum distance is updated to I, as all seats before this occupied seat are empty. For subsequent occupied seats, we calculate the distance to the nearest occupied seat by taking half the distance between the current and the last occupied seat, and update max_distance accordingly. The index of the last occupied seat is updated to the current index. In the second pass, we handle the case where there are trailing empty seats after the last occupied seat. If the last seat in the array is empty, we calculate the distance from the last occupied seat to the end of the array, and update max_distance if this distance is larger than the current maximum. Finally, the function returns the maximum distance found, ensuring that all edge cases, such as empty seats at the start or end of the array, are correctly handled. The solution efficiently computes the result in O(n) time complexity, making it suitable for the input size constraints. Here, we have the Java implementation for solving the problem of maximizing the distance to the closest person. The method max_dist takes an array of integers called seats, where each element is either 0, indicating an empty seat, or 1, indicating an occupied seat. First, we initialize two variables, max_distance to track the maximum distance to the closest person and last_occupied to store the index of the last occupied seat as we iterate through the array. We also store the length of the seats array in n for convenience. The solution involves two passes. In the first pass, we loop through the array to calculate the maximum distance between two occupied seats. If we encounter an occupied seat, represented by seats I == 1, we check if it's the first occupied seat we've found. If it is, we update max distance to the index I, as all the seats before it are empty. Otherwise, we calculate the distance to the closest occupied seat by dividing the gap between the current index and last occupied by 2, and we update max distance to the larger of the two values. After processing, we update last occupied to the current index. Next, we handle the case where there are trailing empty seats after the last occupied seat. This is done by checking if the last seat in the array, seats, n1, is empty. If it is, we calculate the distance from the last occupied seat to the end of the array using n1 last occupied and update max distance to ensure it's the maximum distance. Finally, we return max distance as the result, which represents the maximum distance to the closest person in the given seating arrangement. In this example, we start with the input array 1, 0, 0, 0, 1, 0, 1. The goal is to find the maximum distance to the closest person for any empty seat. First, we initialize three variables. Max_distance is set to 0 to keep track of the maximum distance found so far. Last_occupied is set to -1 to represent that no occupied seat has been encountered yet, and n is set to the length of the array, which is 7 in this case. We then begin the first pass through the array, starting from the left. At I equals 0, we encounter an occupied seat. Since last_occupied is -1, it means this is the first occupied seat in the array. Therefore, the distance to the closest person for this seat is 0, and max_distance remains 0. We then update last_occupied to 0 to mark the index of this occupied seat. At I equals 1 and I equals 2, the seats are empty, and no action is needed, so we simply move on to the next iteration. At I equals 3, the seat is still empty, so there's no action required. At I equals 4, we encounter another occupied seat. Now we calculate the distance to the closest person for the empty seats between the last occupied seat at index 0 and this one at index 4. This distance is calculated as 4 to 0, //2 equals 2. We then update max_distance to the maximum of the current max_distance, which is 0, and this calculated distance, resulting in max_distance equals 2. We also update last_occupied to 4 to mark the position of the current occupied seat. At I equals 5, the seat is empty, so no action is needed. Finally, at I equals 6, we encounter another occupied seat. The distance to the closest person for the empty seats between last_occupied equals 4 and I equals 6 is calculated as 6 to 4, //2 equals 1. We compare this with the current max_distance of 2 and find that it does not exceed it, so max_distance remains 2. We then update last_occupied to 6 to mark the position of the last occupied seat. Now we move to the second pass, which is performed to handle any trailing empty seats. In this case, the last seat in the array, seats-1, is occupied, so there are no trailing empty seats to consider. This means no further updates are needed. At the end of both passes, the final result is max_distance equals 2. This is the maximum distance to the closest person for the given input. Moving on to the next example, we now consider the input 1, 0, 0, 0. Similar to the previous example, we initialize our variables, max_distance equals 0, last_occupied equals -1, and n equals 4, which is the length of the array. As we begin the first pass through the array, we start with I equals 0. Here, the seat is occupied. Since last_occupied equals -1, it means this is the first occupied seat we've encountered. Therefore, we update max_distance equals 0 because the distance to the closest person for this seat is 0. We then update last_occupied to 0 to mark the position of this occupied seat. At I equals 1 and I equals 2, the seats are empty, so no action is needed for these iterations. Finally, at I equals 3, the seat is also empty, so we move on without taking any additional steps. In the second pass, we check for trailing empty seats. Here, the last seat in the array, seats-1, is empty, which means trailing empty seats exist. The distance to the closest person for these trailing empty seats is calculated as n1 last_occupied equals 4 1 0 equals 3. We then update max_distance to the maximum of the current max_distance, which is 0, and this calculated distance, resulting in max_distance equals 3. At the end of both passes, the final result for this example is max_distance equals 3. Now let's look at a smaller input, 0, 1. As before, we initialize max_distance equals 0, last_occupied equals -1, and n equals 2, which is the length of the array. In the first pass, at I equals 0, the seat is empty, so no action is needed. At I equals 1, the seat is occupied. Since last_occupied equals -1, it means this is the first occupied seat. We update max_distance equals I equals 1, as this is the distance to the closest person for the empty seat at I equals 0. We also update last_occupied equals 1 to mark the position of this occupied seat. In the second pass, we check for trailing empty seats. Since the last seat in the array, seats-1, is occupied, there are no trailing empty seats to handle. Therefore, no further updates are needed. The final result for this example is max_distance equals 1. To analyze the time complexity of this solution for problem number 849, consider the two main passes over the seats array. During the first pass, the algorithm iterates through all n seats, checking whether a seat is occupied and performing constant time operations such as comparisons and arithmetic calculations. This contributes an overall time complexity of O(n) for the first pass. Afterward, a quick check is performed to determine if the last seat is empty, which is a constant time operation, or O(1). Since the algorithm processes each seat exactly once, the dominant factor is the O(n) from the first pass, making the total time complexity O(n). Now let's break this down further. Regardless of the distribution of occupied or empty seats, the algorithm processes all n seats in every scenario. This means that the time complexity remains O(n) in the best case, worst case, and average case. Turning to space complexity, the solution only uses a few variables, max_distance, which tracks the maximum distance so far, last_occupied, which stores the index of the most recently occupied seat, and n, which holds the length of the seats array. All of these are constant space variables. Since the algorithm avoids creating additional data structures or using recursion, the space complexity is O(1). Breaking down memory usage, the algorithm does not require additional space for processing the input. The seats array is provided externally and does not count toward the algorithm's space usage. The only memory overhead comes from a small number of auxiliary variables, which are constant in size. By comparison, a naive or brute force approach would involve iterating over every seat and calculating the distance to the nearest occupied seat for each empty one. This would result in a time complexity of O(n²) due to the nested iterations. The optimized solution avoids this inefficiency by performing a single forward pass and handling edge cases with constant time checks, reducing the time complexity to O(n), and keeping space usage at O(1). To summarize, the solution achieves a time complexity of O(n) by processing the input seats array in a linear pass, while optimizing edge case handling with constant time operations. The space complexity is O(1), since no additional data structures are used, and memory usage is limited to a few variables. This approach represents a significant improvement over the naive O(n² solution, providing a highly efficient way to calculate the maximum distance to the closest person. When solving this problem, there are several common mistakes to watch out for. First, be careful with edge seats, like the first or last seat in the row. If the first seat is empty, the distance to the closest person is the entire stretch of empty seats up to the first occupied seat, not half the range, which is a frequent source of off-by-one errors. Another mistake is assuming that the input will always have both empty and occupied seats. While the problem constraints might prevent this, failing to validate edge cases like all seats being empty or all being occupied can lead to unexpected errors in your solution. Inefficiency is another pitfall. Using a brute force approach to calculate the distance for every empty seat to all occupied seats results in O(n²) time complexity, which is unnecessary. Instead, you can achieve a more efficient solution with a two-pass or sliding window approach. Additionally, be cautious when calculating distances in middle segments of empty seats. Dividing the sequence between two occupied seats should use floor division, and forgetting this can lead to incorrect results. Finally, optimizing for large inputs is critical. Solutions that repeatedly iterate over the array or use multiple nested loops can lead to time limit exceeded errors, especially for large inputs with n close to 10 to the power of 4. Keeping these pitfalls in mind will help you avoid common errors and create a robust solution. Now, let's focus on some interview-specific insights for this problem. Recognizing the pattern is key. This is a max distance in intervals problem, so dividing the array into segments like the leftmost empty segment, middle segments, and the rightmost empty segment can simplify the approach. Interviewers often expect you to identify and use an optimal solution, such as the two-pass approach, where you calculate distances left to right and then right to left in O(n) time. This method strikes a good balance between simplicity and efficiency. It's also important to clarify edge cases during the interview. For instance, ask whether all seats being empty or occupied is a valid scenario. This shows you're detail-oriented and thorough. Space complexity is another consideration. While using auxiliary arrays for distances is acceptable, pointing out that the problem can be solved in O1 space by maintaining running variables demonstrates a deeper understanding of optimization. Additionally, this problem is closely related to others on LeetCode. For example, max consecutive ones involves finding the longest contiguous sequence of ones in a binary array, which also requires analyzing segments. Problems like robot bounded in circle and sort array by parity 2 involve recognizing patterns, while baseball game highlights the importance of maintaining running totals, similar to tracking max distances in this problem. There are also a few alternative approaches to consider, each with its own trade-offs. The brute force method calculates the distance to the nearest occupied seat for every empty seat. While it's simple to understand and implement, it has an n² time complexity, making it inefficient for large inputs. A more efficient solution is the two-pass approach. Here, you calculate the distance from the nearest occupied seat in 2 steps, first from the left, then from the right. Finally, for each seat, you take the maximum of these 2 distances. This approach is optimal in terms of time complexity, running in O(n), but it does require auxiliary space for storing the distance array. For even better space efficiency, the single-pass approach is an option. By maintaining running variables for the last occupied seat index during a single traversal, you can update the maximum distance for each empty seat on the fly. This reduces the space complexity to O1, but it's slightly harder to implement compared to the two-pass method. Each of these approaches has its merits, and choosing the right one depends on the constraints and requirements of the problem at hand. Great job! To wrap things up, we reviewed the algorithm for solving maximize distance to closest person, discussed edge cases, and highlighted the importance of linear scans for such problems. Don't forget to practice similar challenges to solidify your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!